and we mentioned different methods that are used, how the image can detect how the camera can detect the image, the edges, the color, um, and all the specification that needed to be detected for the image to be identified easily. All right. So we have what we call the logarithmic dynamic range adjustment. So this is some mathematical formulas or calculations that are actually used in order to get more details about the image itself. All right. So the logarithmic method is just used to for dynamic range adjustment, just like human eyes process signals in the similar way. You know what I'm saying? So yesterday we mentioned the concept of grayscale level. So just to remind you, what is a grayscale level? So basically, the grayscale level is just certain concepts that we use in digital imaging and in AI that will represent the intensity of the light in an image without colors, right? So we just focus on the intensity of the light without looking at the image itself, without looking at the colors image. So grayscale images are widely used in computer vision because they can simplify the whole process, right? So what is a grayscale image? So a grayscale image will contain all the shades of grays, right? Ranging from black to white, right? So we're going to range from black to white. So from black to white, a grayscale image will contain shades of gray ranging from black to white. So each pixel represents only the intensity of light that's at that location. So at that location of the picture, so each pixel represent only the intensity of light at that pixel, not the color. So that will be the grayscale level. Okay, so grayscale is often used in AI when color is not really critical, in terms of just detecting the edges, medical imaging, when we're looking at medical documents, whatever, scans. So the color is not really important for that scenario, but we need to detect the image itself. So in this case, grayscale image is very important. But if we need to analyze an image where the colors can identify what we're talking about, then grayscale is not the good method, right? So when we're calculating the grayscale level, it will just be kind of a numeric value that is representing the brightness of the pixel. All right, so this can range from 0 to a maximum depending on a bit depth. So if we have a 1 bit depth, we go to level 2, right? So the levels, we're only going to have 2 levels. Can anybody tell us why? Why, if we only have a depth of 1 bit, we're only going to have 2 levels? All right, so the numbers of levels of shades from black to gray, the numbers of levels will depend on the bits that we have, the bit depth. So the bit depth, so we're going to take 2 to the power the bit depth. So that means if you only have 1 bit, it means 2 to the power 1, which is 2 levels. So if we have an 8 bit, it means we're going to have 2 to the power 8, which is 256. All right, so the 256 levels, which mean from level 0, so level 0 we will the color black, to level 255, which is the color white. So from 1 to 254, that is the shade of gray that we have. All right, and then we have, if let's say we have a 16-bit, it means we're going to have 2 to the power 16, which will be 65,536. That is really a high precision grayscale, which is usually used for medical imaging. All right, so now we have this logarithmic dynamic range adjustment. So when we talk about logarithmic dynamic range adjustment, this is just a technique which is used in image processing. Okay, when we're doing it in AI, to just improve the visibility of details, right, in images that have high dynamic range. That's for example, we have scenes with both very dark or very bright region on the picture. So this is basically inspired by the human eye perception of light, where we perceive brightness on a logarithmic scale rather than a linear one. Okay, so what is dynamic range? So the dynamic range means that we have the ratio between, the brightness and the darkness part of the image. Okay, so a high dynamic range, or HDR images, will contain details in both shadow and highlight. All right, so AI system may struggle with linear images, where we have dark pixels that are too dark and bright pixel that's really saturated. So that's why we need to do logarithmic adjustment. Why we do a logarithmic adjustment? Because of the way the perception of brightness is. So when we look at the perception of brightness, just like in the human eye, so this is a measurement that is logarithmic more than just being linear. So dark areas are perceived with more sensitivity than bright areas. So the logarithmic adjustment, we just transform the pixel intensity so that we have dark pixels that become more visible, and then bright pixels that can be compressed as well to avoid saturation. So this will be the formula here, where in this formula we have this f of IG, which is basically the original pixel intensity. Then we have G here, which represents the adjusted pixel intensity. So here we've adjusted it, and C will just be the scaling constant, which will usually choose between the maximum intensity to 255 in an 8-bit image, depends. So that's why here we're using the 255, because we're dealing with an 8-bit image. All right, so this is an example of an image after doing an adjustment, dynamic range adjustment. So we have an image which kind of adjusts the pixels. So when we have an input image with certain pixel, we apply a logarithmic transformation to each pixel, and then we will output a picture with better visibility in dark regions. So all the dark region can be visible. So basically, the effect of this will be that the dark pixels are amplified, and then the bright pixels are are compressed. So now we have an overall contrast that appear more balanced. All right. So yeah, so this will apply more in terms of AI. It will apply more in things like medical imaging, computer vision, in terms of object detections, and HDR image processing, where we combine different exposure of for realistic images. All right, so that's what we're going to have there. All right, so we will also have another method which we're going to call image filtering. But before we do that, so when we're talking about the logarithmic adjustment, we can create what we call an histogram that shows the grayscale images based on each pixel, how the grayscale level was. But we're going to see how the grayscale are being calculated. So this is how the grayscale can be calculated, where we're going to have a normalized histogram. To create that, we have Ni over N, which will represent the frequency of the grayscale level. All right, so we have that. This can be an example of different grayscale level at different pixel. For example, here we want to do an histogram equalization. So when we're doing an histogram equalization, where we can calculate the grayscale value for of new images. So we have this image here, which will apply to this. So at each level, this is the grayscale level here. So now the input image is here. So at this, we have the first pixel here, we had a 1. So we take that 1 here. What do we have at 1, level 1? At 1, we have, this is the grayscale level 0.20. And then we multiply it by the numbers of data that we have here. So 0.20 times 9, we have a 1.8, which is approximately 2. So that's what we're going to have in the output image there. So this is what information we're going to have when the picture has been equalized. On that level, we have done an adjustment. Okay, so these are just some examples of the histogram representing that image. Okay, so and then we have image filtering. So when we talk about image filtering, what is image filtering? So image filtering will just be kind of a core concept in AI and computer vision, where we're going to have to modify or enhance an image by just manipulating its pixel value. So usually the goal of highlighting features or removing some noise or detecting certain pattern, right? So this is how human can actually visualize all the edges of objects or the contrast or certain textures. So what will be really image filtering? So this will basically be the process of applying a mathematical operation to each pixel that you have in a certain picture. Especially we consider the other pixel as well around the picture. So we apply a certain mathematical operation to each pixel to try and produce a new image. So filters are usually implemented as convolutional operation when we're using the CNN, convolutional neural network. So the filters are implemented on the convolutional operations of the kernel. All right, so you remember when we spoke about having a kernel that will take the neural network, and we have a convolutional layer which will take we have the kernel that will do certain operation to the pixel of the picture. This is exactly what it means. So we have different type of image filtering. So we can have like an average filter, or we can have a Gaussian filter, you know, an average filter or mean feature filter, where we have, for example, each pixel is replaced by the average of its neighbors, right? So we take maybe one pixel here, and then we take the average of the neighbors of that pictures, and then we're going to replace that value to create the new value. So the new value of that pixel will be the average of the surrounding, right? And then we can also have a Gaussian. So when we have a Gaussian filter, in that case, now we will give more importance to central pixels. All right. So these apply in AI when we're dealing with pre-processing the images for CNN, which is the convolutional neural network. This will, yeah, that's how we're going to actually use that. All right, so that's the image filtering. So we can also get a maximum or minimum filter. That means we take the surrounding pixels, we get the maximum or that. Okay, so this is an example here. We have a picture here. We filter this, so we can easily create new images by changing the values of the images. So when you want to understand that, you understand that we are dealing with image image filtering will just be manipulating the pixel to just kind of enhance or make this picture more smooth or detect certain features from the pictures, you understand? So this is implemented using some kernels, especially in the convolutional neural network. So this is crucial for AI pre-processing, you know, in terms of features extractions and improving the whole model performance. All right, so we can have, as I said, we can have the mean filtering. Mean filtering, it means that we are taking the average of the data, all right? And then we have the median filtering. So median filtering is just one of the type of non-linear image filtering, which is also used in AI and computer vision. So this will help with noise reduction while preserving the whole edges of the picture itself, you know. So with here, we're going to take each pixel, which will be replaced with the median value of the neighboring pixels. So the median, as you know, we're going to see whatever is the middle of the numbers. So unlike the mean, we're going to take the average, right? So with the mean, unlike the mean filters, the median does not blur the edges of the pictures. So, which is making it ideal for preserving the details of the image. So the median filtering is commonly used because of this reason. So in this case, we're going to choose, let's say, the window size. So in this case, for example, we have we can have a 3x3 mean filtering that we've done to this image to get this one. And then from there, we can do a 3x3 median filtering. So that's 3x3. It means now, in this case, we are actually, this is the windows that we want to use. So the numbers of pixels we're going to use, because remember, one picture can have so many pixels. Because remember, if the size of the picture is maybe 28 by 28, it means in total we have 784 pixels. So now we have to take certain portion of the picture. So If we take a 3x3 window, it means we're dealing with those 3x3. That means those data that we have there. We're going to find the mean or the median. All right. So the window size can be chosen. It can be a 3x3, 5x5. So that will determine the pixel that need to be processed. Okay. So you need to understand that we can collect all pixel intensity values inside a certain window, and then we can sort the value and then get the median, and then we're going to replace the central pixel of that window that we took. We're going to replace it with the median value from the sorted list. All right, so that's exactly what is going to happen. So yeah. So some advantages of the median filtering is that we're going to reduce the noise for the picture, and then we're going to preserve the edges, which is better than the mean and average filters. So it works very well for grayscale and color images. But the disadvantage is that we can slightly reduce the fine textures, details, if the window size is too large. If you take a window size too large, then we kind of reducing the textures of the image. All right. So this is used in object detections, in medical imaging, where we actually we can remove noise from ultrasound images, X-rays images. All right, so that is one of the reason why that is used, right? So we can also have a maximum filtering. So can anybody tell me what's the window size of this picture? Window size that we're taking to calculate the maximum or minimum filtering here? What's the maximum size? And what's the window size? Guys, what's the window size here? Guys, this is very easy. Is there anybody who doesn't know the window size here? Is there anybody who doesn't know? Or is there anybody who knows?
I say it has to be all of them added together.
Sorry?
I'm saying it must be the sum of all the pixels.
No, I'm asking about the window size. All right, so the window size is 3x3. So we have a 3x3 window size that we took here. And the values of the pixels, these are the values of the pixel. And what we're going to do, we're going to sort them in a proper order. And then from here now, we can get the maximum value. So in this case, the maximum value will be the 150. So the maximum value will be used for the middle.
Okay.
Okay, so what we're going to do, you see, like this is what we have. So we take this. So this all window here is to determine the new number that will be here, to adjust it, to do a filtering. You see now, for now, the value here is what? 150, right? So we take every other pixel of the neighbors, these pixels here. The lowest is this one, 98. We go up to the highest, which is 144. So now that we have all this, so what is the maximum? What is the highest? The highest will be 144. So the value of 144 will be now the new value. So when we have the new image in this pixel here, the machine is going to replace the 150 by 144. So the new value in the new image will be 144 instead of 150. You understand, guys? So that's what it means. So in this case, we're doing a maximum filtering. If we were doing an average filtering, then we're going to take these numbers, find the average, like add all these numbers divided by the total of them, find the average, and then the value that we're going to find, that's what we replace here. So that's what's so this is the maximum filtering. So that's what the maximum filtering does. So it looks for the maximum of the neighbors and then replace the middle. Okay. So we can have certain properties of image differentiation. That means we can have first order differentiation or second order differentiation. It means when we're looking at a constant grayscale area, the differentiation value of the image is 0, example, and then the differential value of at the start point of the grayscale slope step or slope is not 0, and then the differential value along the slope is not 0. So that will be the case of the first order differential. And then we have the second order differential where we have a constant area. The second order differential value is 0, and then the differential value at the start point of the grayscale or slope is not 0, and then we have the differential value along the slope, which is 0. So those are what you call image differentiation. So we can have certain operation here. Just have some formulas. Okay, so this is how the image filtering can actually affect an image. We can have an original image like this. After doing an image sharpening, in this filtering, we obtain this type of image. Right, these are we can also have edge detection here, which we're going to have through an algorithm. So sometimes we can use certain algorithms such as the Gaussian filtering or the canny. So the canny will just make the edge thinner. So when we talk about the canny edge detection algorithm, so this is just one of the most widely used edge detection methods in computer vision, right? Which is just designed to detect sharp intensity changes in images, which will actually correspond to the edges of the image. So the main purpose of this the main purpose of this canny edge detection is just to detect the edges in an image, which will basically represent the boundaries of the image. So this will help AI system, for example, to identify the shape, see that, okay, this we're talking about, we're looking at a rectangle, like a circle, or different type of shapes of a certain object. All right, so we have about 5 steps. Here. So where we're going to use the Gaussian filter to just smooth the image and reduce the noise. And then we're gonna have to calculate the gradient intensity and direction of each pixel in the image. All right. So when we're doing the gradient calculation, where we're going to actually compute all the intensity gradient of each pixel using certain operations, right? Where we check maybe the gradient magnitude, to see the age strength or the age or orientation. Understand? So we have different steps that are going to be used to just try and transform the pictures. All right. So yeah, I think that will be all for this will be all for today, guys. I'm just going to look at I want to show you something. Just to show you what you call this. So I want to make you understand what is an image window. Especially for those who did not do, oh yeah, this is the right image I can show. For those who did not do HCIA, I think this may be a misunderstanding somewhere, but if you've done HCIA of AI, you will know when we did, we use a convolutional kernel to actually get the image thing. Okay, so look at this image here. I'm not too sure if I can make it bigger. Let me try. No, it's avoiding that it sends us to a different page. Okay, there we go. You see, so think of this as this is the kernel that will deal with that. So when we're looking at this, we take this window. Can you see here? It's taking a 3 by 3. It means it's moving 3 by 3. A group of 3 move the next group of 3, and then goes down, group of 3. So in those group of 3, if you're doing an average, it's going to do exactly what I told you to get the average around and gets the one in the middle. If it's doing a maximum, it's going to calculate the maximum. If it's doing what you call this, a median, it's going to do the median. So that's how we're going to get the full image there. All right. Any question on this? Any question? Any question on that, guys? Yes?
No questions on my side.
Yeah, this is exactly what it's doing. For example, in this case, we have a red, green, and blue. So we have the RGB model here. So it's looking at the picture and seeing how much of so this is when we make the whole picture that we have. So when we take the full picture, we do a scale of the range of red. So so all the shades of red in 200 maybe and 56 levels. At each point of the picture, we see which shade of red we have on that point. We do the same thing for the same picture. The shade of green, we have the full pixels there. And then we have the shade of blue. So now these kernels, like the first kernel channel, will deal with red and create an image of that. So the final image will be a 3 by 3. And then we have the shade of green as well, 3 by 3. And then these 3 values here will give us the final values of the image And these values are the ones that are going to be used in AI calculations. All right, guys. All right. So if there is no questions, I think that will be all for today. I will see you on Tuesday. Thank you very much.